Welcome to the AWS for AI podcast.
Welcome to AWS for AI, the podcast where we explore cutting-edge AI solutions and the innovators behind them. I'm your host, Hamza Mimi, AWS Solutions Architect. Our guest today is Anton Alexander, a leading expert who works with the world's top large model builders as AWS's senior specialist for worldwide foundational models, with focus on scaling large trainings and inference workloads with AWS SageMaker Hyperpod. He's a veteran CUDA programmer, Kubernetes, Slurm, NVIDIA expert, but also a Brazilian Jiu-Jitsu and collegiate boxing champion. In this episode, we'll explore the trends, challenges, and evolution of foundational model trainings. We will explore some of the tools, tips, and tricks for building models at scale. And we will dive deep in some of the deep knowledge that Anton brings to the table. Anton, I'm really happy to have you with us today. Welcome to the show.
Thank you. Ahlan wa sahlan.
Shukran. So before we go into the technical discussions, can you tell us a bit about your story from Trinidad and Tobago to New York to the University of Maryland and now to the AWS AI space?
I was actually born in the Caribbean island of Trinidad and Tobago, which is quite unique because 50% of our population is East Indian. They were the indentured laborers that came from India during the British colonization, and my father's of African descent. So I'm mixed. My mother's Indian, my father's Afro-Caribbean. And my mother came to the United States as a nurse in the 90s to New York, and then she eventually moved to New Jersey, Bethesda Medical Center there. And I had uncles, they were engineers in the oil and gas because Trinidad, we have oil. And my uncle was an automations engineer. And we always he had a computer. And my other uncle lived with us and he had a computer. He was going to Rutgers. He's a chemist. And my uncle Alan, he worked for Exxon at the time. He always had computers around. So, my cousin Gary, he bought me a Nintendo. It was my first video game and I got really into gaming. My mom moved to Maryland because they had really good public schools. I went to middle school, high school in Maryland. I was in a tech magnet program. I got really good at computers, but I was really obsessed with video games. So anything to beat the game, I was all for it, right? And then I got into PC gaming and they had GPUs. Oh. So I started building my own computers. Back in the day when you had to burn CDs, I got into, configuring, building my own PCs and things. And then I went to University of Maryland for engineering. And then, I started doing private work, contracting. I had my own company. I went back. I got another degree in mathematics and computer science. And then after that, AI became hot. And I had a friend, he was actually a lead at the NSA. And he hired me for a position at a startup and it was funded by Mike Jank. He's a former SEAL Team 6 commander. Oh. He funds Data Tribe. Shout out to Data Tribe. They fund a lot of the leading cybersecurity companies in America, period. Mike's a veteran. He invented the black phone silent circle. I was there. That's during the COVID time. I became really popular on Clubhouse. So I would have thousands of people come to speak. Eric Weinstein, Lex Friedman would come, Guillaume Verdun, the creator of TensorFlow Quantum. Yeah. And somebody from Saudi heard me talking one time. And one of the companies that was with us, Dragos, Mike funded them as Rob Lee. He was a former NSA guy too. He got like $200 million in funding. And so I was like, man, this Saudi thing doesn't seem bad. He got it from Aramco, right? I think it was $100 million, right? So I was like, this Saudi thing doesn't seem bad and AI is coming. So I might as well go. Let me check it out. So I went over there. I ended up staying there for a little while. I worked with them, worked with Sadaya, Abdullah, Tabi, he's a great guy, Yasser, all those guys there. They're awesome. They were doing some really good work. Alam, I helped on the Hajj and the Mecca project. I got special permission to go there. And the facial recognition, the the crowd counting, right? So I'm Muslim too, so it's pretty cool, right, to contribute, right,
to be there.
to be there. And Abdullah, Yasser, appreciate them, by the way. That was like amazing opportunity. And then I got an offer from AWS. The GPU restrictions came in, so it was like a little bit harder to get access to the GPUs. And then I came to AWS after that. Yeah.
And the rest is history.
Yeah.
Just for those listening to us, SEDAIA is the Saudi Data and AI Authority.
Yes, exactly.
And
Yeah.
they are the builders of models like LLM and
Yep.
and some of the most Saudi innovative work.
Yep.
You spend a lot of time in mathematics.
Yeah.
How did that help go into AI?
Man, it's the foundation of AI, or just like thinking in general. I think that mathematics kind of forces you to think in a way where every step has to be kind of like proven or validated, right? And you have different mathematics. You have theoretical mathematics. You have mathematics that can like diverge, and in these more control, which was bounded above and below, like monotonic Kachi type, or things that just oscillate, right, within this finite space. That's kind of like where I kind of like operate, right? Linear algebra or finite spaces. Just deducing that and, proving things and just having that mind state, it's very beneficial, right? When you're calculating different things like model sizing, inferencing, you're working with a customer who's building a custom model from scratch, right? And you kind of got to help them. They might be researchers, right? And they're trying to calculate the size of the cluster, or it might be somebody that's trying to take a model into production and they're trying to size their workload. So having that experience, as well as like the computer science, engineering experience, it all, comes together, especially with AI.
And with that, now you talk to a lot of the foundational model builders.
Yeah.
Before AWS, but especially at AWS, all over the world.
Especially at AWS. Yeah.
And let's dive deeper into what the most challenges that you see with these kind of customers. If you're building a large foundational model, what kind of problems you need to solve?
There's several problems, right? We'll put them into buckets, right? So let's talk about training the model, right now, what the challenges are. Because the researchers are doing the building, right? Us as Amazon, we're the infrastructure, right? And you have the network, right? You have the compute. And those are generally the two components, right? Because for distributed training, which is much different than other types of training, these are large models. So you have to distribute the weights or the brain of the model over multiple nodes. And you have to decide what type of orchestration you want, Kubernetes, Slurm, right? Some people can do this bare metal as well if they have access, right? But for us, we offer, Slurm, Kubernetes, you can go on EC2, right? And configuring that, step one, right? Drivers, CUDA drivers, CUDA DNN drivers, CUDA toolkit drivers, Nickel, which is the communication library from NVIDIA. You have MPI, message passing, how that works, right? The EFA, how EFA integrates. So the versions, the drivers, all these things have to be in sync. And then above that, the layer above that, you have your frameworks, right? And you have PyTorch, you have TensorFlow. PyTorch is pretty popular, right? And then you have your distributed training framework like NeMo, Ray. There's Puther, Colossal AI. You have DeepSpeed, right? And they all have trade-offs, long context, different libraries that are available. So one of the challenges is like just stitching that all together. I think at Amazon we do a good job of that though. Especially my team, we deal with the largest customers, so we see a lot of their pain. So like we've created software and services to kind of like address those, especially GPU failure. So if you read the Lama paper, Lama Herd of models, you go to page 13, you'll see that during the training of Lama, there were almost 500 interruptions. And even Meta faces these issues, right? It's the number one thing, right? If everything is smooth, the only thing you really can predict is if this GPU will fail, right? Because Jensen and these other GPU makers, right, NVIDIA, AMD, different ones, we have our own Trainium as well, right? They're getting down to, 5 nanometers and below, right? And those transistors and those physical hardware, as they get smaller, right, it's a lot more that can happen to them. The probability of them, right, due to heat, due to different things, right? Even bad programming, like somebody didn't size a model too much. It's utilizing the GPU, but not utilizing it all the way, right? Yeah. So those are like the challenges you kind of like encounter during training, right? The right decisions, frameworks, making sure drivers, everything is aligned from the software side. Then you have hardware things, and even the network interface cards, right? They can have problems, and the configuration of the NICs.
So you have different personas handling different problems. You have, in general, in these large foundational model builders, you have the infrastructure team, DevOps team, basically managing that. Yeah. Network layer, infrastructure layer, and then you have the researchers thinking about the framework and the defining the loss function and the deep technical aspects, and then you need to have some sort of data management. Let's tackle different aspects. Okay. From the IT infrastructure side of things. You mentioned the Herd of Models paper from Meta. What are we seeing in AWS when customers work with AWS? Basically, we have similar kind of workloads. They still have similar problems. Are there different problems that were not covered in Meta's Herd of Models?
I would say the problems that Meta had are ones that we do see with customers, but the scale that Meta was training at is a lot larger. So it's a little bit more. They had more problems that can happen, right? Because the scale of the training, right? I think those problems exist, but sometimes the simpler problems happen, like where it's like I spoke about CUDA. Or just somebody didn't program something right?
That's not in the Meta paper.
That's not, Or like with nickel, right? Like you have to set the size of the packets, right? And you have jumbo frames, you have you have like the average MTU, which is 1500, right? And then you have jumbo frames, 9,000, right? Like most people don't know this type of stuff, especially like, you might be an AI guy, you don't know networking. That's why for my team, we pretty much have to be in every layer and good enough. Like, cause we're dealing with the smartest, top researchers, biggest customers in the world. So the problems that can happen can range across the entire spectrum of problems, right? We see everything, every problem, right? Pretty much the number one problem, though, that customers kind of want to address is just failures. And sometimes it's really hard to debug. We call them gray failures, right? Because there's a trade-off. Like when you're monitoring a cluster and you have all these monitoring hooks inside the cluster, you're actually taking up network bandwidth, right? And you're polling that unit, and you're basically, you're using clock cycles of the CPU and the GPU, right? So these are clock cycles, and you don't get them back, right? So you got to kind of make the trade-off of like what you really want to see, and being able to configure the machine even to diagnose the failure is hard. So we call them gray failures. That's a general term, right? So to even say like, hey, this failure happened, you have to have enough data to form a hypothesis. And a lot of times right now, is not that granular, right? Of data.
And gray failure also cover failures with nothing works and failures where performance is impacted, but it's still kind of working.
It's still kind of working.
And it's very hard to know if it's just something that's impacting slightly the performance or like a node failure. So we'll dive deep in how we solve kind of these problems. But before, let's go to the other problems. I know we talked about the hardware part, but what are you seeing in the pure research AI level?
Okay. Yeah, good question.
I know you talk to a lot of
Yeah.
model builders.
Yeah.
What are the trends and the things that currently people are working on?
I think mixture of experts parallelism,
No.
right, and asynchronous communication with that, right? So, and on the inferencing side, disaggregated inferencing. At first, inferencing was coupled together, right? The pre-fill and the decode phase, right? So NVIDIA introduced NeMo, which allows you to basically decouple these phases to make it faster. So you could separate them and they're not sequential anymore, right? With models, we're seeing these mixture of experts, right, at scale.
Yeah.
And they present a new type of networking paradigm, right? And they present a new type of strategy when it comes to the memory allocation, right? And then with the GB200s and the B200s with the unified memory, especially with the GB200s, the actual all the compute sitting in a one rack via NVLink and stitched together via NVLink is kind of cool, right? And it presents a new challenge and a new paradigm. But with the CPU architecture, it's also a challenge for people to overcome, right? Like you might have a new GPU, you might jump from the H100 to the B100 and just kind of like adapting your code to these newer GPUs. Because what happens is they introduce new floating point precision.
Yeah.
Right, and the floating point precision is the number of bits, right, and how they're represented, right. So as you change and you introduce new floating point precisions, they're new floating point operator, the graphs or the way that the math is done, right. It shrinks it, and your memory space, the allocation of the memory changes as well, right. So you have to adapt and optimize, and new functions get created, things get optimized. So just navigating through that with these new GPUs is kind of one of the challenges I see.
So just to go back to the mixture of model architecture and try to explain that. So the mixture of model is basically trying to have multiple small models communicating together with specific knowledge in different areas.
Exactly.
That brings also condensation of energy, of training. So if you're training on a large data set and only one of these smaller models or one of these clusters is heavily involved in that particular training, you'd have potentially large portion of your GPU cluster not working. How do you navigate that?
Yeah, interesting question. All right. So the job is to essentially distribute things evenly.
Yes.
Right. And when you're monitoring the cluster, you want to make sure that the memory, the VRAM of the node is essentially utilized to its maximum capacity. Mixture of experts, basically, you can kind of do that. There's methodologies to do that by correctly adopting the right training policy. Now you have FSDP, DDP, you have hybrid strategies, right? And when you're training these models, right, the job of the infrastructure / like research dev guy, right? He's like a guy that has to like understand all of this. So there's one guy, right? Or not a group of guys or girls, right? Yeah. And you have to be able to know the networking implications if you're multi-node training. You have to calculate the distribution, right? So if this data set or this like potential like stress on one model, right, can be more, that goes down to your pre-calculation. You can kind of figure these things out or know them before for training. So the things you would know is you would know how many tokens your data set is. and you would know what groups, categories of data sets you have. And you would know your context length, how big, the slices of the data going in, right? And you would know how many epochs or views of the entire data set you would need. So once you have this base calculation, and back to the mathematic thing, right? And different things like your hidden layers, your attention, your V stands for vocabulary, the permutations of all the tokens, like how many tokens, how big is your vocabulary of this LLM, right? And you can kind of calculate this. So the person that's training can essentially know, hey, how to distribute this across the nodes. And so that's where, the customer, they kind of know this, right? And the more advanced customers, right? And the customers who want to use models like this, we kind of make it easy for them by creating recipes. So we have like Hyperpod recipes where everything's kind of pre-configured for the customer and we guide them through it, right? They're Kubernetes, they know GPUs, they're not academic researchers, and they kind of want a turnkey solution. So we're able to provide that. Even for the more advanced customers, we do provide that layer of resiliency because you have two personas, right? You have the researcher who's not a DevOps person, but then you have the DevOps person, who's not a researcher, right? So we kind of cater for both. We offer, there's advantages on both sides. So, but again, it's about doing the due diligence and the calculations because it's a finite mathematical space at the end of the day.
One of the things we were discussing earlier is I want to build a model and I know it's going to be a 1 billion or 100 billion parameter model. I know the kind of data I do want to use. I don't know how many GPUs do I need. Is it 100 or 1,000?
Yeah.
How do you answer these questions? I know your team does this work as well.
Yeah, our team does this. I have a colleague, Pavel. He built our model estimator, right? And it's a science, right? So you have the parameters, how big your model is, like X amount of parameters, right? Then you have like your hidden layers, which is essentially like the kind of like the vector space or like, how big the model kind of like mathematically looks, right? Then you have your attention layers, right? And because you got to calculate the parallelism as well, right? You have your V, which is the vocabulary. And then you have your context links, like the windows of this, right? And you're trying to use all these things that to calculate something called like the VRAM, right? And in this VRAM, the total memory you need has to be distributed based on a strategy, which is FSDP, DDP, or whatever, right? And you have sharding techniques. So how you distribute the model over the GPU, right? So you do the calculation and you figure out your strategy, data parallelism model, all these words you guys probably hear, right? And girls hear, right? So based on these calculations, you would then determine your VRAM, right? And once you know the VRAM, you can kind of pick and choose which policy can be used to train a model. You also have to figure out if the model can be distributed because some of the layers might not support that. So transformer-based architecture does so, right? But you might have like a UNet architecture or other model architectures that aren't inherently able to distribute. You might do other strategies to get it to do that. So the distribution across multi-node, right, is the thing. So being able to kind of like support that. And the networking communication layer has to be there in order to distribute. And we have these things called all reduce, all gathers, all to all. These are network functions. NICO handles that, NCCL, right? It's the NVIDIA communication library. And these are all factors. So all this has to be considered, right? And to basically determine the amount of GPUs that you need.
Once you define that, and that's a lot of calculations, and then there are also some elements of, do I want to, so the win versus lose if I distribute more or less. Do I want this to take more time and take some hypothesis about how fast my loss function is going to converge.
Yeah.
And then you define that. Let's suppose we decided on a size. Then we start launching our training, right? All the people that are working on large foundational models, their life basically once the model is launched, they're checking all the time.
Yeah, checking all the
right?
time. Yeah, tensor board. You're looking at
Yes.
watching that loss function converge.
Exactly.
Yeah.
Can you talk a bit about what are they checking? What are they doing once the job is launched?
Man. So I remember the early days, computer vision days, like MobileNet, ResNet days. You'd have like your tensor board, right? So there's different things, right? The most important thing is loss.
Yeah.
Right? Loss is just a simple mathematical formula. It's the square root distance between the actual truth and the predicted value of the model, right? You take the input of it, you multiply times the weights, right? It's a vector operation, X input times W hat, which is the weights, plus or minus the bias, and you get Y hat, which is the predicted value, right? Then you measure the distance between that, which is the loss function, Y squared, minus Y hat squared, right? Square root, right? And your job, the AI model's job is to basically reduce that distance, right? It's trying to minimize the loss between what is true and what it predicted, right? And then it changes its weights while it does its gradient descent process, right, to basically localize the minimum, right? So it's basically trying to say, hey, how can I minimize this loss by shaking up these weights and moving them around? And that's what this person is looking at, and they're just like sitting there like it's basically you're sending this AI through test after test after test after test, and you're just saying, hey, is this guy improving his grade? Right? It's like watching your kid grow up, right? So, and you're just sitting there watching this loss function. And that leads to a good point. Like, so when you go to sleep, right? Sometimes trainings crash.
Exactly, yeah.
And, you're frustrated and like you go to sleep and you wake up and like your trainings crash and you're like, man, but what happened, right? So at AWS, we do like have a solution for that, because that's one of the pains customers feel. The research scientists, they're looking at this all the time. And with us, right, so with Hyperpod, we've seen that. And we've been able to address that issue with like node recovery, failure recovery, and resiliency that we bake into our clusters that allow our customers to kind of like know when they go to sleep that when that model is training, they could at least wake up and look at that loss function back again, right?
How you define your loss function, that's your job.
Yeah.
And how the infrastructure works, that we can help with, right?
Yeah, exactly. We can help.
Yeah.
All right. So like you wake up in the morning, at least you got something to look at.
Yeah.
Yeah, not a crash system.
Exactly.
Yeah.
So one of the things that comes back again and again is when I talk to model trainers is I'm looking to my loss function. I'm looking to how fast or slow it is conversion, if it's conversion.
Yeah.
But also I'm looking to check if it failed.
Yeah.
And I need to restart this because I'm losing $1 million every amount of time it's not running.
Yeah.
And there basically is where Hyperpod comes, right?
Exactly.
Can you talk about what's Hyperpod?
Yeah.
And how are we solving these problems?
Yeah. I'll be glad to. So Hyperpod is the voice of our customers. It literally is the voice of our customers. Our customers at AWS, when generative AI first started, they come to AWS. We are the leading cloud provider. We invented cloud, right? So they come to Amazon and they are trying to run their workloads on us, right? And for everybody, including Amazon, are training models, right? We have our own models, Nova, that we use, that our customers use, the AI every day our customers use. So there's a lot of experience from our customers and internally. And we saw a couple of issues that is across the entire spectrum. It's what we just spoke about. When you train a model and something happens and you're watching this all the time. So Hyperpod offers basically the ability to diagnose that cluster and these nodes with health checks, deep health checks before, and continuous monitoring during the training to identify certain types of failures that occur in a cluster. And we take these unhealthy nodes and replace them automatically. And we automatically resume the training from that checkpoint. So we find the faulty nodes, right? If the node fails, hardware failure is like the most popular failure, right? These things are hot. You never know, the GPU might fail, right? We're able to export metrics that allow us to basically see this. And then if it fails, we automatically automatically resume the training from the checkpoint. So if you're sleeping, you know that this is happening, right? And then our libraries, our entire stack is built on the common frameworks that all the researchers and scientists that we talk to and we've seen over, years of doing this, they use, right? So it's a challenge installing, managing, and implementing these frameworks because it requires GPU software, drivers, communication libraries, host drivers, EKS, or some whatever orchestration tool you're using. So that comes prepackaged. So it's like EKS out the box. You don't have to be an infrastructure expert, right? So you can actually train your large distributed model as a researcher, right? And also the other side is as an infrastructure person who's not a researcher, who wants to build an AI model, who's been using AWS and Kubernetes, right? It's easy for you to come and do large scale distributed training because all those libraries management is already done. And we have recipes that's verified for a lot of our larger customers, our 3P partners that launch their models on Amazon, like Meta, we have Mistral, even DeepSeek. So pre-training and fine tuning them, we have scripts that they can run, 2 or more DevOps guys and girls. They can essentially run this and, makes it really easy for them. So both personas, we kind of address the pain of both our customers.
And the fact that we are trying to solve this, we learn more about it. And you mentioned already the gray failures.
Yeah.
Obviously, automating and managing the infrastructure for hard failure is undifferentiated heavy lifting, and we're now at AWS to remove those.
Yeah.
But how are we also trying to manage the gray failures? What are the things that we are looking at from Hyperpod perspective to make sure we're capturing also failures that are not node failing?
Yeah. So there's failures that happen, right, where you don't know what happens.
Yeah.
It just fails, right? But we can look at certain things that we're able to export, right? So it's like your car, right? You think about it like this. You're driving from point A to point B. We'll just kind of position it like that. Now, there's 2 things that can happen if your car's having a problem, right? One is that your check engine light comes on, right? And hey, there's a problem, but like you're not hearing anything, you don't know, so you don't know what the problem is, okay? There's actually 3 situations, 3 permutations of this, right? The other is that you hear something and the check engine light comes on. So hey, that's a problem, right? Then there's the check engine light doesn't come on, but there's a problem, right? And you might not be able to notice that problem, right? But if you monitor it a little bit more closely, you can see that you might not be speeding up or speeding down as fast as you were, right? The check engine light's not on, but your speed might not increase or decrease as it should, right? Yeah. Let's think about that like network communication, right? You see some fluctuations and things like that in the network. So with those permutations, right, we look at all 3 of them, right? We have the experience. So we're looking at things that might be anomalies, right, in the training. And that allows us to identify based on our experience, right, does this look anomalous? Like this is outlier, right? And then from there, our agents that are running, right, will detect that and flag it, and it will start watching. And once it reaches a certain threshold, we replace the node.
And once we identify those, is there an impact? What happens? We identified we have a problem. We know because we have better visibility in different things, and we're aggregating those, and now we know what happens there.
Yeah. So you have aggregated this data, right? So this is how, the Novas, the Claudes, the Chat GPTs, all these big models are running, right? And this is the holy grail of AI, is kind of like automating this thing. So you detect the problem, which is really hard to do, by the way. Super hard, right? Even you see in the paper from Meta, they have grade failures where they're like, hey, it's just a hardware failure, quote unquote. They don't tell you what type it is. So that just shows you, and those guys are amazing engineers, right? One of our team members is from over there. So you basically, once you find out that there's something, an indicator, right? So I'm driving my car, and let's see, I hear something, or my speed is not accelerating like the way it should, right? Or the check engine light comes on, right? But the check engine light might not come on. But I have to determine, is this car unsafe now, right? So I can look at properties of the car, like acceleration, noise, sound. I'm looking at that same thing in GPUs. And once we find that at that threshold, we replace it. So what happens is that when you submit the job for training, right, we have a mechanism where the customer submits through Kubeflow or something that we're integrating in, and we have hooks, right? And so you have your data set, it's already tokenized, it's sitting there in a FSX. You have your training scripts, it's sitting there, right, on a head node or some storage unit. And you have your checkpoint, which is continually being saved. So if your job fails, literally all you have to do is just run the command that started the training, because everything's there. So we will replace the faulty node, add it back into the cluster, and just restart the training.
Transparently from end user perspective.
Yeah. And the compute sits in the SageMaker account, right? So we can orchestrate that, because if it was on the customer's account, we couldn't really, right, orchestrate it. So
what indicators are we optimizing for? I know we're optimizing for the mean time to completely repair. We spoke before about
mean time to replacement.
To replacement, to detection. What are the metrics we're looking for, and how can we optimize for each? Yeah.
So one of the things I was saying, GPU failure, I'm like really good at that, right? So that's my thing. I think that for me, and the way I look at it is that I think about it as like a car, right? Traveling. And that analogy I use, like you have check engine lights, right? So there's a methodology called a use methodology, right? Utilization, saturation, and errors. And when something's not operating right, you're going to see something. You're going to see fluctuations in the tokens. You're going to see some type of like pullback, right? It can be operating right, but overheating, right? So you have to have hooks into all the possible things that can happen during training. And once you have these hooks in, you can look and start seeing things. Like you could visually look and see like, okay, this training, I have token fluctuation here, right? I have 1,000 node cluster and these tokens are fluctuating, right? What could it be? Oh, it's either thermal throttling, right? A GPU, one of the ranks is getting, a rank is a GPU essentially, right? Is getting throttled, right? Or it can be some like network issue, right? Or it can be a storage issue, IOPS, right? So sometimes the NIC can get hot and overheat and leak over, ambient heat leakage. You can have the network card is not performing right? You're maybe using like some high speed storage and like, it's not delivering right. So that's a great fit. You don't know, something happens, right? But if you have hooks into the right places, you can kind of see what's happening. But there's a trade-off, right? Polling and passing all these messages for all these devices over the network while you're training can impact the training, right? So you have to make a decision into the hooks or the KPIs that you're looking at and their impact on the distributed training. So that's a science in itself.
Yeah.
And you got to be really good at it because it does have a direct impact.
That will help you reduce the time to detection of a particular problem. But there's also the time to restore from that last checkpoint.
Yep.
And checkpoints is another science.
Yeah. That's a science in its own self.
Can you talk a bit about the best practices for checkpoints? What do you see work? And how do we help customers with those?
Yeah, that's an interesting question. So checkpointing is getting really advanced. So you have checkpointing before was that you have these network operations, right? So when you're doing, I'll focus on distributed training. This isn't like one node training, right? So when you're distributing training, you have either parts of the model that's sharded over the entire network, right? Or you can have different copies of the model, right? All over the network, right? Depending on your training strategy. And you have these functions going on by nickel, these all reduce, all gathers, all that's collecting and distributing these network functions, right? And collecting data and doing that. So most of the time you're saving this checkpoint on like a S3 or FSX. And if your training happens, crashes during that time, right? You have to start back from the old checkpoint. So let's say, your training crashed, so you got to go back. So now we have things like asynchronous checkpointing, right? Where you can basically start from different positions in the checkpoint, right? And you have in-memory restarts, right? And you have techniques where the system itself, right, the NVMe, you can bind it to a persistent volume claim. So you get the high-speed memory, right? And essentially the state of the system, if it can be saved, you can basically restore it from that state. And that's where people are trying to go to right now, right? Is being able to do that. So by using the local memory and saying the old paradigm was like, hey, we save this checkpoint, it crashes, we resume from the checkpoint. But now it's like, hey, what was the state this training was at when it crashed, right? And even now people are saying, hey, can I remove this rank? So with Nickel, NVIDIA introduced something new called this communicator and this unified memory, where if a node fails, you can actually remove it from the ranks, right? And continue training. So yeah, it's pretty crazy.
And so just to finish on the checkpoint aspects. So first, the old trainers from 2 years ago, that's old now.
Yeah.
You just have a checkpoint every 3 hours or something.
That's it.
And you send it over the network and that's it. Now we're doing the asynchronous checkpointing. And we have also the option to get in-memory checkpoints.
Yeah.
And wherever we're trying to recover, we'll check if we're able to get that memory, if it's not a total failure. If not, if we can, which is most of the cases, we'll just use that. There is no impact on the bandwidth, and we just go from there. And then we have the async. I've seen some studies where it doesn't impact even the network.
No,
when you're doing
async,
the async.
Yeah.
So yeah, crazy.
Yeah. And restartless training. So where you don't even have to restart, they just remove it recovers, right? Because when you configure the training, the node size, the VRAM, all that's important, because if a compute node leaves, right, your VRAM calculation is messed up because you have your batch size, your content link, you have all of this is calculated. So now there's an ability to even remove a rank and kind of adjust in real time on the fly. So that's even interesting in itself too, right? So at our team, we're pretty versed in this stuff. We're on top of it. We're at the bleeding edge. We deal with this every day. This is what our customers is doing. And we're just trying to stay ahead of the curve and solve for all these challenges and all this innovative technology.
One of the things you're really focusing on is the monitoring aspects, and you've already talked about the use methodology. Something that we discussed before is the focus on utilization.
Yeah.
Um,
Yeah.
it may not be the best metric. Can you explain why?
Yeah. This is a great question. And I love to explain this to people, right? Especially computer programmers. Once you explain it to them, they get it, right? So you'll hear everybody, you'll run NVIDIA -SMI and you'll see GPU utilization, right? And everybody's on my GPU running training is utilized all the way, right? But there's a methodology we have in computer science for real diagnosis, which is use, right? Utilization, saturation, and errors. Utilization in GPU, right, is this. I can write a function in CUDA, and for all my old school C++ programmers, you can do memalloc or CUDA memalloc and allocate that memory, right, which is a pointer to the kernel space. I'm saying I need this much memory, right? And I could do a while loop that does nothing, or I can do a while loop that does something, but they're both utilizing. You'll see the same utilization.
100%, yeah.
Right. So there's no difference in if that function does nothing or if it has code that's running. That is utilization. It's just saying I'm utilizing this. You think about it like you have a room full of, let's say, CUDA cores, right? So I have this room full of CUDA cores. And let's say these CUDA cores are like bikes, right? So I have 1,000 bikes in the studio. I'm going spin class, right? But I just sit on the bike and I'm not spinning. But that bike is being utilized, right? So that bike at this space is 100% utilized, right? No. So, but nobody's spinning the wheels. No. So that's what saturation comes in, right? Saturation is basically the amount of work that's being done in that kernel space, right? Or you could also, there's another view that says like it's the amount of work, the amount of work you can throw at it. Like, so like I have more room or I don't have room. It's fully saturated, meaning it can't take any more work, right? I need more memory.
And by combining basically, it still is a useful information to have utilization, but also combining it with saturation.
Yeah.
And the error rates, you basically have that full visibility and you can take the right decisions. What kind of use cases where utilization is 100%, but you're not really using that? Mm-hmm. And what actions would you need to take?
Yeah, great question. So when you're writing, people are writing custom kernels or custom graph operations. And these custom graph operations, they might not be written efficiently, right? They're new to CUDA. CUDA's unforgiving. It's C, C++, right? That's I've been programming C, my first language.
Yeah, pointers are crazy.
Yeah, pointers, addresses, double pointers, right? Yeah. And CUDA's that line that's in that space, right? Because it's like it's an extern C language. So when you write it in C, you'll see C, and then you'll write extern, and these curly brackets come, and you spin up these CUDA kernels, right? You allocate these kernel spaces, and when you basically you have full control, literally, right? And as you're writing these mathematical operations, you can be wrong. Yeah. Just like you're writing a math equation for a test, right? There might be an easy way or a simple way to solve the problem. So like in computer science is the asymptotic complexity, right? So asymptotic complexity, you can solve a problem, but it can be very complex. Like it could be, n squared, right? Right? Or you can basically be log n. And like it's like these sort problems, right? So depending on that complexity, or you could do nothing, like it just be one, like right. One. So like or zero, whatever, right? But that's it. That's what it is. So depending on how good the programmer is who's writing this kernel, it dictates how well they can utilize the kernel space.
And by monitoring these metrics, you know how good is your programming as well.
Exactly, in
you
your
can
model.
optimize
Yeah,
that.
how optimized your model is. You can that's when we talk about like FP8, FP16, mixed precisions, right? That's why mixed precisions became popular. So it's all about the essentially the optimization of the code, the mathematical operations, making sure that they are as optimized as possible to derive at the outcome that you're looking for in the least amount of steps or the most optimal mathematical computational sequence.
We talked about a lot about the training aspects, but these problems also apply to inference.
Oh yeah.
And inference is also a different beast.
Oh god. Yeah.
How does Hyperpod also solve inferencing problem?
Yeah, great question. So GPU failures happen. Scaling. Hyperpod for inferencing, it came out of, once again, at AWS, and people ask me, they say, Anton, why'd you come to Amazon, right? And really it's the listening to our customers and being customer obsessed. One of our leadership principles is disagree and commit. And it's like healthy for us to disagree and have a different idea. And especially in the GPU space and the AI space, we all have our opinions, right? And like you have grade failures. So grade failure is something that there's not enough information for you to be exact and like say, hey, it was this. You can make a hypothesis and a best guess, right? Yeah. So somebody might say, hey, it might be this, might be that. And you can disagree, right? And it's the same thing with inferencing. And inferencing is scaling out massively because everybody's been training models and now they're trying to do inferencing, right? But with inferencing, you have the scaling of inferencing, and inferencing workloads can change. So you have to have auto scaling, right? So it's seasonal in the night, in the morning, depending on the country and things like that. So managing that workload, right? And being able to optimize for that and being able to predict the size of the compute you need. It's not like training where it's pretty much static, right? But inferencing, the workloads are seasonal. And then when a failure happens during peak time, how do you manage that, right? So if a node goes down, it's not like, hey, I could stop this training and like come back in a couple hours. No, these customers are trying to use this. So you have to be able to do intelligent routing. You have to have tricks in the background to accommodate for the inferencing workload, right? And now with inferencing, right, we had Nickel, but now there's new libraries like the DPP library from DeepSeek. DPP rewrote some of the InfiniBand, like firmware-ish layers. And you have people optimizing the actual hardware firmwares or patches into these hardwares to optimize for inferencing. You have SG Lang, they're doing optimization. Now you have, we had quantization, right? Yeah. But now we have FP8, right? Which is, think about that. It's like, hey, I have a floating point and I can move the digit around while I'm inferencing, right? So I can shrink this model down and not really lose anything, right? So you have all these considerations. If I shrink this model down, now we used to quantize, right? But now, okay, I don't need to quantize anymore. I can do FP8, basically same bits width, essentially, kind of, but, and get still a floating point, right? And how does that impact, right? If I change my mixed precision, if I change my precision or I optimize my layers for different precision, what's the am I still as accurate? And what about if I were doing evaluation, the things I didn't see, how good are they going to perform? So inferencing is a big science.
It's also where we used to see large clusters of GPU mainly used for training. Now GenAI applications are everywhere, and we start seeing large clusters for inferencing.
Yes.
And these are different problems.
Some
are the same. The hardware is the same. But do you see in these kind of use cases any similarities or like I know the hardware failures, but do you see any similarities in the kind of challenge that customers use Hyperpod to solve both, or are we building different kind of features specifically for inferences?
I think for the inference part of it, especially with like the GB200, which is ARM based, and it has the NVLink, there's a different type of resiliency that you can bake into inferencing workload versus a training workload. And I think for our customers, that's where the benefit is, right? Our experience doing that. The networking part of the load balancer, when that request is coming in and something happens, right? Making sure that the customer doesn't experience latency or downtime or quality of service. So that, once again, right, we're customer obsessed. Our customers are customer obsessed, and the impact of the customer is the number one thing. So that's the difference. And the resiliency factor here is a little bit more robust, and you have to think about the other components like the load balancer, intelligent routing, KV cache, right? Caching, prompt, storing prompts and things like that. So it's like that the memory,
different kind of knowledge, and at the end of it, you don't have a researcher looking at loss function. You have an actual customer that is trying to buy something. So it's different.
And latency, the latency, the customer wants it fast, reliable, correct, right? So that's where the resiliency feature kind of shines when it comes to inferencing, and that's where we're really good at that. This is what we do every day to our customers are the largest customers in the world, and their customers are our essentially, our customers. So it's on us, right, to make sure we're the entire chain.
One of the things maybe I want also to touch on is the NeMo ecosystem, and in particular the recent launch for the NeMo agents. Can you talk a little bit about what that was fascinating for me, having agents that basically an MCP enabled agent that basically monitor also your NVIDIA workloads. Can you talk a bit about what's that?
Yeah, it's amazing. We were at that workshop. I was with my counterparts, so we work closely with NVIDIA. They're our partner, right? And one of my the adjacent team, my man, I work with them too. Prabha, she's my manager basically on the NVIDIA side, and Shuba on the Hyperpod side, and we work closely with our customers, right? And we work closely with our partners, and NVIDIA is one of our partners, right? They have a software ecosystem, NeMo, which is very popular, and our customers use it for distributed training, right? They use it for data creation, NeMo Curator. They're using, Triton, and this whole ecosystem for developing AI. And recently, I seen something that NeMo launched with this NeMo Agent Toolkit. And what they're doing is that, so if I was a startup or I was an organization and I had a large cluster and I wanted to monitor this thing and take action, I would have to have, like, I can watch with CloudWatch, I can watch with Prometheus Grafana and get metrics all day, but how do I take action and how do I dive deeper, right? I need somebody that specializes in that to do that.
Understands that.
Yeah, understands it. But now you can have an agent, an LLM configured that's looking at these things. And as long as you have the ability to extract the information, they can kind of make choices and decisions and observe and, take action from your data that's coming off of your cluster. And that's a very interesting paradigm to me because that switches up the way startups can scale. Customers can, be self-sufficient and enabled, because our job is to enable our customers, enable our partners, right? And having this tool would allow us, like our customers now could run their AI agents on AWS, and the AI agents could be helping them,
and
analyze their workloads and things like that.
And that researcher we talked about, they will just configure their
Yeah.
MCP agent,
Yes.
and they will go to sleep.
Yeah, exactly. That researcher is now he has a DevOps agent,
Exactly.
right, running,
and they can sleep a bit more. I
yes,
guess.
exactly.
Before we end, I want to ask you a final question about you talk to a lot of model builders. You've seen in the last few years how AI evolve. What do you think are the most trends to look for in the next coming months and years? And where do you think AI is moving in the training, building of AI, but also in general in AI?
I think that GRPO was one of the most monumental things of our time. I think the entire DeepSeek team actually did amazing work. DPP is a library for network communication where they made some changes to the network communication libraries. I think that GRPO, which mixes in these inferencing, right? It's not like when you do DPO or ORPO, you have one like during the forward pass, right? You have one inferencing where you kind of like do the inferencing and it gets the Y hat, right, the predicted. And what GRPO did is like scaled that, and that was pretty interesting to me. And it allowed a customer to get a model to the level of ChatGPT or state of the art, but significant less money. So our customers at first said, hey, man, if I want a ChatGPT, I'll have to spend $100 million or $1 billion. Now it presents an opportunity for our customers, right, to do. I still believe in CPT. I read the research. People have this idea that fine tuning is it. I think that if the utility of the model, you have more shelf life with CPT than with fine tuning. I've seen this across several models. Like it's pretty self-evident, right? And then you do like CPT with a high quality data set and a generalized data set, and then a fine tuning, right? But it's going to shift to fine tuning and these optimized fine tuning tactics that can get you state of the art quality. Then the next thing is visual LLMs and three-dimensional LLMs, where you're looking at 3D data, point cloud data, real data, right? Into like this quantum space, right? That vector space is 3D. And you're able to talk to it and get insight, like seismic data or molecules or like compounds and things like that. And then VLLMs, visual LLMs, the ability to like write a note, right? And basically multimodal visual LLMs, like that whole like ensemble of models that can essentially like fit on your phone or live in your house. And like you can start like monitoring your food, water, everything, right? It's gonna give us real-time information and the ability to do analysis that we never seen before. So I'm looking forward to that. The optimization of LLMs, basically,
amazing. The future is really exciting, and I'm sure we will be amazed by tomorrow's announcements and tomorrow in the general sense. Thank you very much, Anton. It was really an exciting discussion to have you today, and hopefully we'll have you again in some other time.
Looking forward to it. Thank you very much.
Thank you. With that, we have reached the end of our fascinating discussion with Anton. We've covered crucial insights about scaling foundational models and practical solutions for common challenges in AI. As you've heard, the tools and infrastructure for building these models continue to evolve rapidly. For more AI learnings and exciting discussions, subscribe to the podcast and leave us a rating and review. And as always, until next time, this is Hamza Mimi thanking you for listening. Keep exploring, keep innovating, and we'll catch you on our next episode.